All right, here's the deal. So this is one of our new topics. It's not really all that new. It's not really any different than what we've been looking at. Matter of fact, some of you might find it easier. The only thing that students tend to struggle with this is kind of visualizing the solid. Okay, so what we're looking at is volumes of solids with known cross sections. So that's what we're going to look at here. Now, I'm going to post this entire presentation, which really is just a couple problems, but it has a link right there, GeoGebra visualization, so you can use the same visualization that I'm going to show you. And really the goal of that is just so you can see the solid that we're talking about. So let's go ahead and get started. So sample problem for this, and this would be exactly the wording that you would see on the AP test. As a matter of fact, I just modified the question here, but I did not modify the wording. So it says, let there be a region R enclosed by the graph of y equals x squared and y equals the square root of x. Okay. Region R is the base of a solid, so it's really the bottom of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. So we've got some cross-sections or slices, right? Think about that. Like our cross-sections before with the rotational solids were circles. But we've got some cross-sections that are squares. And it says that the cross-section has a side in R. Find the volume of the solid. So just like before, we need to really start to look and see what this looks like. So here is a graph of the region R. I just brought this up with Desmos. And so we've got this region, and it says that this region R, which is really right in here, is the base of a solid. And it says for this solid, each cross-section perpendicular to the x-axis. So what does that mean? So cross-section, slice, right? We know we're taking a slice here. So that's a slice. Perpendicular to the x-axis. So we're slicing, our knife is kind of cutting perpendicular to the x-axis. And it says, for this solid, each cross-section or slice perpendicular to the x-axis is a square with a side in R. So here's the thing, nothing new in terms of this. We're still finding volumes, so we can still use our nice little acronym. And this stuff's going to kind of appear and disappear as I toggle between controlling my computer and whatnot. So what we really need to do is we need to start to picture it. So we have this picture of what the base looks like, and I can kind of see, you know, because we're slicing it, I can kind of see where those slices are, those rectangles, right? So the rectangles are going to be in here, right? Because that's really where the slice is. That's the base. And we need to take this slice, so what does this slice look like? It describes it, but the hardest part for students is to visualize it. So let's go ahead and do that. Let's create some visual of this. So what does it look like? So what you can see here is we've got our graph over here on this side right here, right? We've got our graph here. And then we have this three-dimensional rendering right over here. And so what you're going to see is as we start to play with this, you'll see kind of what it looks like in the graph, and you'll also see what it looks like on the three-dimensional rendering. Now, notice also right over in here, we have the ability to say, hey, what the cross-sections look like. This one's going to be set as squares because that's our problem. So, but you have the ability to kind of look and see what would it look like if they were equilateral triangles or semicircles also. So let's go ahead and look at a slice. Right now, it's set up so that X is really where it's taking the slice. And if I move X, you can start to see, right, and I can toggle this out. So you can see there's this slice, right, because we're slicing it perpendicular to the X-axis. The X-axis is the red axis in this case. So here's the slice that we had on our previous thing, right? That's the way our knife is cutting. And you can see it's in that region, right? And that's where the slice would cut. And if we click on square, it's really showing us what that slice is going to look like. So keep in mind it said each cross section is a square with a side in region R. And so inside of this, we can see this idea. The side is in region R, but the slice happens to be a square. So we've got one side in region R, and then it's made into a slice. So it's kind of built up, you know, just like that. And that's what our slice looks like. Okay, so this is what the slice looks like, but what does the solid look like, right? Like, think about this. We could take slices all the way through, so I'm just moving where that slice is. But if we had all of these slices, it would make a solid. So let's start to see what that might look like. Now, n really controls how many slices it's going to be showing us. And as I make n bigger and bigger, you can start to see all of the slices, and you can start to get an idea for what the solid's going to look like, especially when I go all the way. So there's a ton of slices, you know, 100 slices. And we can actually take this and we can kind of rotate our three-dimensional solid. Keep in mind the green axis is the y-axis. The red axis is the x-axis. So there's the graph from the top view, right? And then as you start to rotate it, you can see, you know, and not surprisingly, that as we move along the x-axis, right, those slices become taller and taller and taller, and then all of a sudden they start to become shorter and shorter and shorter and shorter. And again, keep in mind, this is because the slices are squares, right? We just can't see this on the back side, whose side is in region R. So that's kind of like a slice right there, right? So they get really fat in the middle, and so they get really tall in the middle. And then they get really, really skinny, not very tall on the end, because, you know, at the end, the side isn't all that big for that square. And so we can see the side's not all that big for the square. We got these little tiny squares. So this is what the solid looks like, right? We can see that again, like, right? You can play around with this if you want to understand it. This is what the solid looks like. So keep in mind what we're trying to do now is we're trying to find the volume of this solid. So let's go back, kind of think about when we're finding volumes of solids, we can use our acronym, PERSEVI, right? And again, this is just to break down the problem into smaller chunks. We've talked about the ideas of this. So we have this picture, right? We want to draw the rectangle. We know we're slicing it perpendicular to the y-axis. I don't like when I froze it. Sorry, people. So, you know, PERSEVI. So our slice, right? If we draw that rectangle, that's where it's going to be, right? If I actually draw it as a rectangle instead of just a little slice. I'm going to have to erase where I just went too far there. Kind of get the idea. And then you have to imagine that this is built up at you, right? Because that's really what it was doing. It was kind of coming up at you. And so if I take this slice and I pick it up and I kind of lay it down, what we're going to see, right? They told us what we're going to see is we're going to see this idea of a square. So that's if I pick this slice up and set it down. And so maybe what I'll do is I'll kind of show you that that's kind of that bottom leg. And all I've done is really kind of picked up this slice that was built out at you and kind of laid it down flat. Kind of like, just imagine it's a domino and you push it over, right? So that's what we're seeing. So, picture, got it. Rectangle, got it. Slice, got it. Area, I need to know the area of one slice, because big idea, to find the volume of the solid, we're just going to add up all the slices. That's that whole integration piece. So what do I know about this slice? Well, you know, for one, I know it's got this tiny little thickness, right? Tiny little thickness. It's like a cheese slice, right? So we've got this tiny little thickness, right? And we can see that thickness right there. So that's that thickness. But we've got that green line. Well, that green line is really the size of the side of the square. So how big is that green line? Well, that green line is just a difference in two y values, right? So the question becomes, where are the y values. How big are the y values? So what we'll do, go ahead and look at that. And what we know about this is the y value up here, we know y is really the square root of x. So really this spot up here is the square root of x tall. Right? And then down here, for the blue one, we know that that height is really, x squared tall. Because that's the equation y equals x squared, and then the red equation. And so really, we want a difference of the y values. We want to know how high the y value was up here, subtract how high the y value was down there. So let's go ahead and figure that out. That green line is really just going to be the square root of x subtract x squared, right? Because distance is difference, right? We know that acronym. Right? So maybe I'll write that down over here. Distance is difference. So I'm taking the difference of those two to figure out how far apart they are. So that's how far apart they are. So then let's go back in our acronym. We're trying to find the area. Well, that's the size of a square. So I could always just, I know that this is going to be the same thing. And so I know the area will be really the root of x subtract x squared. And we're going to square it, right? The whole idea of where squaring comes from. All right, cool. So we've got the area of a slice. But it's not really just the two-dimensional shape. It's got a volume. So we need to know how to make this thing the volume. So keep in mind, since it has that tiny little thickness right there, that's why it has volume. So come back over here. What's that little thickness? It's dx. So if we take our area and multiply it by our depth, or width, whatever you want to call that for the slice, now it's become a rectangular prism, or a square prism in this case. Now we have the volume of that, right? Area times how high it's built up. So now we have our volume. And then we still need to come up with this integral. So let's go back and we're going to integrate this thing. So we're adding up all the slices from where to where. Well, think about it. Where did we start making these slices? Well, if we were to slice this, I would start making them over at x equals 0, and I would keep making them all the way until x equals, 1. And if I didn't know where that was, right, I could always figure it out by figuring out where these two things intersect, because that's really where it's going to stop. And so this integral is a way for me to find the volume of this solid. I've got my area of a single slice made into a volume, and then add it all up for Sevi. Picture, rectangle, slice, area, volume, integrate. And this is how we can find the the volume of that three-dimensional solid. Hope this helps. Play around with it, kind of go back and forth in the video, play around with the visualization. I'll post another one on a different solid as well. So hope you guys are all doing well. Take care.